So as far as videos that have started playlists so far this semester, that's probably the most odd video that you're going to see to start off a playlist. So let's get to the actual point of what I was trying to show in that last video. So the concept for this section is related rates. Now I wanted to consider the growth rate of the balloon. As the helium was being pumped into the balloon. So here's time. Here's our perception of the size of the balloon. So right as you see that first initial puff of helium into the balloon, it looks like it expands very rapidly. And then over the course of the time that we're pumping more and more into it, it's still getting larger, but it seems to be doing so at a considerably slower rate. So my question is this. If the helium is being pumped out of the tank and therefore into the balloon at a uniform rate, why doesn't this look like it's getting bigger at a uniform rate as it's being pumped in? So here's what we know. Helium is pumped into the tank. No, pumped into the balloon from the tank at a constant rate. Now with that in mind, when it comes to our perception of the size of an object, especially a three-dimensional object, we equate that to only one dimension. We tend to talk about the size of things relative to just their height or their length. Now, in a three-dimensional sense, the mistake that we make with this is that something that appears twice as large might have, for example, a diameter that is twice as large or a radius that is twice as large as something else. Now, with that in mind, the three-dimensional quantity that's associated with that volume would actually be 8 times larger. So what we're going to do is try to relate the one-dimensional quantity associated with a balloon with the three-dimensional quantity of the volume of the helium. So let's assume that the balloon is approximately spherical. Now, if we assume that the balloon is spherical, then the volume of said balloon is going to be equal to 4/3 pi r cubed. This is the volume of a sphere formula. So as time progresses, both the volume and radius are getting bigger. Now, when something changes over the course of time, that means technically they could be interpreted as being functions of time. So volume is actually a function of time, and r is actually a function of time as well. So here's what we're going to do to this. We are going to treat volume and radius as though they're a function of time. We're going to differentiate with respect to time. Now what that means is, on the left-hand side, we'll get the rate of change of the volume with respect to time. And on the right-hand side, we would need to use implicit differentiation and the chain rule. The 4/3 pi is a constant multiple, so we'll treat it as such. But the r cubed is going to be 3r squared times the derivative of r with respect to time. This derivative represents our perception of the rate at which the size of the balloon is changing. Now, simplifying the right-hand side a little bit, this will be 4 pi r squared times dr over dt. We also said earlier that the helium is being pumped into the balloon at a constant rate. That means that this quantity, dV over dt, is just some constant. We'll use k for that constant. Now, if we solve this relationship for dr dt, we are going to get whatever that constant rate flow is divided by 4 pi r squared, which, for the record, 4 pi r squared for a sphere represents the surface area of the sphere. Now, the interpretation that we can give to this statement is that as the radius is getting larger, this fraction is getting smaller, meaning that the rate at which we perceive the size getting bigger is going to be smaller if the radius is bigger. So as the radius increases, the size rate decreases. So it still looks like it's getting bigger, it just looks like it's getting bigger at a slower rate of change. Now, what we did in all of this is we were considering the relationship that exists between these two different rates of change, the rate of change of volume with respect to time, and the rate of change of the radius with respect to time. Put these together, and these are known as related rates. Got to make sure that's actually on camera. These are known as related rates because quite literally they are two derivatives that are related to each other. Derivatives being rates and that equal sign being a relation. So over the course of this section we're going to be analyzing lots of different rates of change, and I can just about guarantee that all of the rates that we're going to see are going to change over the course of time. So be prepared to do lots of implicit differentiation with respect to time.